Hi everyone, this video is to introduce you guys to our fun math game, Rocket Math, where the main real-world application would be to teach grade school students math in a fun, competitive way.
Here on the FPGA is how you start the game. So the start button is the center button, and as soon as I press it, the timer will go off. The answer to 0 plus 0 is 0, and I'm going to type it on the keyboard. 0, enter, and that resets this as soon as I click enter. The next answer is 9. I'm going to type 9, which updates over here. As I click enter, again, it updates to a new question. The questions will also update automatically when the timer runs out, so 10 seconds for each question. There we go, and the points also update automatically. So we got 5 questions right, and we got 5 points right now.
Okay. In our single digit function, it's possible to change the game modes. So here we have 3 plus 3, but we can change that to subtraction and do 3 minus 3. So you click 0, adds a point, enter for a new question, and then 7 again. It's also possible, so back to addition, we can do 10. And then for multiplication, we can switch this second key and go into multiplication. So 3 times 2 is 6. Hit 6, the light lights up, a point is added, and enter for a new question. When you get an answer incorrect, points are not added, and the correct answer LED is not lit up. So 3 plus 4 is not 9. But if I click 9 and enter, nothing happens.
And here's our double digit screen. As you can see, it randomizes all 4 numbers on the screen, and you can do multiplication, addition, and subtraction.
This is our multiple choice screen with 4 multiple choice options. This is one of our addition problems, and then when we switch the screen, it shows another addition problem, and the correct answer choices change as well. In order to change the mode, it's possible to flip another switch in order to turn it into subtraction, and then this is a second subtraction equation.
And we also have multiplication questions.
So now I'm going to show how we can switch the VGA screens using the FPGA. So we have 2 game modes. The first game mode is a free type using the keyboard, and then the second game mode is a multiple choice. So if I flick the switch right here, it changes. I'm going to flip it back. And now we're back to the multiple choice. So in the middle of a gameplay, if you try to click the start stop button again in the middle of like the round, it will take you to game over because that's cheating. So I'm gonna do it right now, and there we are, game over.
So we decided on the VGA display for our game, and we had to use a clock divider to get it down to 25 megahertz instead of 100. And what it does, it just iterates through every single pixel on the screen using a horizontal counter and a vertical counter. So what we did is hard code each individual block on the screen. So for example, the white square is showed in the top right corner, how we did that. And then we did every single one of the ABF for the 7th segment. We did the same exact thing, and then we put that into a case statement so we could display the numbers from 0 through 9. So how it works is that we have a 1-bit register that we put to 1 if we're inside the specific range we want to color, and then inside this always block we set that pixel equal to a different color every time we want it to. And here you can see the screens for the multiple choice and the game over screen. We also have a case statement for the signs, plus, minus, and multiplication.
I worked on the keyboard first, so this is just a regular keyboard.v file. I added nothing special. It interprets the bit stream that comes in through the 1-bit keyboard clock and keyboard data. The only things I added were a backspace and enter flag that are output, and I recognize them using the key code that I interpret here. So the get keyboard val.v file uses the keyboard module, and it outputs the cathode display that I interpret down here. It outputs the user answer that I calculate over here, and I multiply it by, I first multiply it by 10 over here, and then I add the new display key. If you type in 1, 2, it's going to be 12, and then I also output the enter flag. The enter flag goes into FSM, and it eventually goes into top to detect when the user has clicked enter. So every time you click enter, it resets to a new question. So here is top, and I wrote the finite state machine in top down here. And obviously you have the idle state, which is this, it's waiting for user to press enter. Then you have the begin state, and the begin state resets either when the user clicks enter, so the new question flag is connected to the enter flag from keyboard, or it resets every time 10 seconds have passed. And then you have the game over state down here. So we have 3 VGA modules depending on what screen we're using, and the way we decide which one to use is we have wires for every single one of them, and we decide which ones to use using the FSM and then the multi-mode condition, which is the switch for whether or not you're playing the multiple choice or the free answer.
The code for our pseudo-random number generator. It uses an idea called an LFSR, which is a linear feedback shift register. That basic idea I'm going to explain using this image right here. So this is for a 3-bit function. We are using a 12-bit number, but the general idea is that some of the bits are XORed with one another, and then these are fed, and all the bits are shifted to the right once, and this XORed function is added on to the end. This chart depicts that. It is pseudo because after it runs through all the bits, it ends up repeating itself. But with a 12-bit number that we are using, there are 4,095 number options. So this is as randomized as it can get. Our XORed function is shown right here. With the feedback register, we XOR 4 different bits in order to maximize the randomized version. And then this is our shift register right here that ultimately ends up shifting the function. The original code generates a random number every clock cycle, but for ours, we want to generate a random number whenever the generate input is initiated. So that code is depicted right here. This simulation just shows how randomized this is. So random is the linear feedback shift register and how it is shifted to the right once. This is not exactly randomized, but the random num is what is fairly randomized. So it waits for all of these to be calculated, and then it outputs a value based on the overall calculation. It is further randomized with our generate input. The random num is only saved when generate input ends up turning off.
Here's our top module. You can see here we have all of our inputs and outputs, and then all of our wires. Our top module is the regular equation screen, and then we also call our random number generator, which generates A and B, and then our FSM and our ALU, which compares, and then our answer check, which compares the result and the entered value. Is our debouncer in our game state. This determines if we're generating a random number or not. Here in the ALU, we have our addition, subtraction, multiplication. It basically takes in the random number generated A and B, and then does the operation and then outputs the correct answer. Here in the answer check module, we have input result and input KB result, which is the entry from the keyboard, and then it generates right if the result is that the ALU generated is equal to the keyboard result entered. So right is 1 if that is equal, and 0 if it's not, meaning it's wrong. And then in that case, it would take away a life as well. Next, we have our simulation for our answer check module. You can see that right goes to 1 when the answer from the result is equal to the keyboard result.
Overall, the project was definitely a success. We were able to have multiple VGA displays, and we could switch screens from VGA multiple choice to the normal equation screen or to the game over screen. And the keyboard input is functional, and when you press enter and it's the correct answer, you get a point, and the LED lights up. And then we're also able to connect the random number generator to the VGA to get the randomized equations. And the ALU and the answer check perfectly works and checks that we're inputting the correct answer. And our failures, mostly due to timing constraints, is that we haven't yet connected the ALU and the keyboard and answer check and everything like that to the game modes for double digit and multiple choice. We started doing switches for the multiple choice answers, but then we didn't have time to finish it. And then the lives are not functional as of now.